Good morning. So let us see the relationship between the Young's modulus and the shear modulus. So this is the relationship between the Young's modulus and the shear modulus. C is equal to E divided by 2 into 1 plus 1 by m, where E is the Young's modulus and C is the shear modulus or modulus of rigidity or rigid modulus, and 1 by m is the Poisson's ratio. Let us do some numericals on this. So these are the numericals which you're going to see now are taken from the Strength of Material books by R.K. Bansal. So these are the exercise problems. Let us learn how to solve the problems. A rod 200 centimeter long and of diameter 3 centimeter is subjected to an axial pull of 30 kilonewton. If Young's modulus of the material is 2 into 10 power 5 Newton per mm square, determine stress, strain, and the elongation of the rod. So these are the given datas. Okay, these are the datas given to solve the problems, and you have to find the stress, strain, and the change in length or the elongation of the rod. And the solution, stress is equal to load by area. So load is given in the problem 30,000 Newton and pi by 4 d square. D is the diameter 30 mm and stress is 42.44 Newton per mm square. And strain is equal to stress by Young's modulus 42.44 divided by 2 to 10 power 5. You get 0.000212 is the strain. And the strain is nothing but change in length by vertical length, that is delta L by L. So delta L is equal to E into, that is strain into length, 0.000212 into length 2000 millimeter, we get 0.424 millimeter. Next problem, find the Young's modulus of a rod of diameter 30 mm and of length 300 millimeter, which is subjected to a tensile load of 60 kilonewton, and the extension of the rod is equal to 0.4 millimeter. So these are the given data. Okay, so we have to find the Young's modulus. So the formula is delta L is equal to PL by AE. Okay, PL by AE, circular rod. So pi by 4 d square is the Young's modulus or area. So Young's modulus is 63,661.97 Newton per mm square. Next problem. The safe stress for a hollow steel column which carries an axial load of 2.2 into 10 power 3 kilonewton is 120 meganewton per meter square. If the external diameter of the column is 25 centimeter, determine the internal diameter. Okay, so we have to find the internal diameter. Okay, so this is the given 120 meganewton per meter square. I have converted to millimeter. That is 120 Newton per mm square. The load is 2.2 into 10 power 6 Newton. Outer dia 250 millimeter. Okay, stress is equal to load by area. Area is pi by 4 d naught square minus di square for a hollow steel column. So from this, stress is given, right? It is 120 megapascal. Load P is given, D naught is given, and you have to find only DI. So DI is equal to 197.88 millimeter. Next problem. An axial pull of 40,000 Newton is acting on a bar consisting of three sections of length 30 centimeter, 25 centimeter, and 20 centimeter, and of diameters 2 centimeter, 4 centimeter, and 5 centimeter respectively. If Young's modulus is 2 into 10 power 5 Newton per mm square, determine the stress in each section and the total extension of the bar. So this is the figure that we have drawn according to the statement, problem statement given. Section 1, Section 2, Section 3, 20 mm dia, 40 mm dia, 50 mm dia, and their respective lengths. It is subjected to an axial tensile load of 40 kilonewton. Now, sigma 1 is equal to P by A1 to find the stress in section 1. Sigma 2 is equal to P by A2 to find the stress in section 2. Sigma 3 is equal to P by A3 to find the stress in section 3, where A1, A2, A3 are the cross-sectional areas for section 1, section 2, section 3. P is nothing but 40,000 Newton. So we just substitute the values A1 and P. We get sigma 1 stress in section 1 is 127.32 Newton per mm square, and sigma 2 is 31.83 Newton per mm square, and sigma 3 20.37 Newton per mm square. Then how to find the total extension of the bar is given by dl is equal to p by, that is dl is equal to pl by a is the formula. Since we have three sections, we are having three terms here, right? E is constant, it is made up of a single material. So P by E we have taken outside, L1 by A1 plus L2 by A2 plus L3 by A3. Okay, so we know that, or else we can write like this also, taking P inside. P by A1 is nothing but sigma 1, P by A2 is nothing but sigma 2, P by A3 is sigma 3. We can write the equation in terms of stress also. So dl, the total extension or total elongation of the bar, is 0.25 millimeter. Next problem, a brass bar having cross-sectional area 900 mm square is subjected to axial forces as shown in figure, in which AB is 0.6 millimeter and BC is zero point 0.8 meter and CD is 1 meter. It is subject to loads as shown in the figure. We have to find the total extension or total elongation of the bar. Young's modulus is 1 into 10 power 5 Newton per millimeter square. So now let us draw the free body diagram for the individual members AB, BC, CD. Now for AB, 40 kilonewton load is acting. So on the other side also it should act the same load, same nature, tensile. Then going to the right hand side, 10 kilonewton compressive. So left hand side also same load, same nature must act. So it is compression. The middle portion, if you take at B, 70 kilonewton is acting right hand side. So at B, this is the point of contact, okay, where these two members AB, BC will be connected. So 40 is acting right hand side. The given problem statement, 70 kilonewton is acting right hand side. So 70 minus 40, 30 kilonewton must act on the member BC so that it would be in equilibrium. So 30 kilonewton acting right hand side, same magnitude and same nature must act on the other side also, 30 kilonewton, which is acting left hand side. Compression. Now you can see here 20 kilonewton is acting left hand side in the problem. Okay, so 30 minus 10 is nothing but 20 kilonewton. That must take the direction of the higher value of force, that is acting left hand side. So 30 minus 10, 20. 20 will take in the same direction of 30. Okay, so now how to find the delta L? Delta L is nothing but summation of PL by AE, PL by AE. So here everything is given in kilonewton. I have converted to Newton by taking this 10 power 3. Okay, so A is nothing but the area. Its throughout area is constant. E is also constant, and this is nothing but P into L, 40 into L, length 600 millimeter, and this is compression, so minus 30 into 800 minus 10 into 1000 millimeter. So we get delta L to be minus 0.111 millimeter. Next problem. Remember, ABCD is subjected to point loads P1, P2, P3 and P4 as shown in figure. Calculate the force P3 necessary for equilibrium if P1 is equal to 120 kilonewton and P2 is equal to 220 kilonewton and P4 is equal to 160 kilonewton. Determine also the net change in the length of the member. Take Young's modulus E is equal to 200 giganewton per meter square. Now, in order to find out the force P3, we have to write down the equilibrium equations. That is, sum of the left-hand side force is equal to the sum of the right-hand side force. That is, P1 plus P3 is equal to P2 plus P4. So from this, we get P3 is equal to 260 kilonewton. So elongation we are trying to find out, that is a net change in the length of the member. The formula is given by summation of PL by AE. Now draw the free body diagram of all the three members AB, BC and CD. AB, P1. P1 is the force 120 kilonewton. Same magnitude, same nature must act on the other side. So it is in tension. Now go to the right hand side. P4 is nothing but 160. Left hand side, same magnitude, but in opposite direction, tensile. The middle, you can see at B, P2 is acting. P2 is 220. So 100 plus 120 is nothing but 220. Okay, so here P3 is 260. Now here 160 is acting, so I should get 260 here. So if I add 100 with this 160, I'll get 260. So the same direction of P3 and it will act. Okay, so 100 plus 160, so 260. Now dl is equal to pl by ae formula. Okay, so kilonewton is converted to newton 10 power 3. E is the Young's modulus 2 to 10 power 5, and P is load 120. Length is 0.75 meters, so convert to millimeter 750 divided by the cross section of this section 1 is square, so 40 into 40, and here it is compression, so that's why it's negative. 100 into 1000 divided by 25 into 25, and the third one is third section, sorry, third member CD. This is tension, right? So 160 into plus 160 into 1200 divided by 30 into 30. So 0.547 millimeter is the net change in the length of the member. Next problem. A steel rod of 2 centimeter diameter is enclosed centrally in a hollow copper tube of external diameter 4 centimeter and internal diameter of 3.5 centimeter. The composite bar is then subjected to an axial pull of 50,000 Newton. If the length of each bar is equal to 20 centimeter, determine the stress in the rod and tube and the load carried by each bar. Young's modulus for the steel is 2 into 10 power 5 Newton per mm square, and for copper is 1 into 10 power 5 Newton per mm square. So these are the given data for the steel rod, and this is for the copper tube, and the load is given, total load is 50,000 Newton. So for a composite bar, we know that total load is equal to sum of the loads carried by the individual members. So here the same expression is written in terms of stress. Load is equal to stress into area. So load carried by steel is nothing but stress induced in the steel into the cross-sectional area of the steel member, plus load carried by the copper is given by stress induced in the copper tube multiplied by the cross-sectional area of the copper tube. So diameters are given. We can just calculate the areas. Okay, so keep it as it is. So we know that the strain is also same for a composite bar if it is having same length. Here it is given to be same length. Strain is nothing but stress by Young's modulus. So stress by Young's modulus of steel is equal to stress by Young's modulus of copper tube. So ES and EC given, that is Young's modulus for steel and copper is given. So if you just write it, and sigma S is equal to 2 times sigma C, substitute this in this expression. Sigma S substitute in terms of sigma C, find out sigma C, then substitute the sigma C here to get sigma S. So this is the answer. Sigma S is equal to 108.36 Newton per mm square, and sigma C is 54.18 Newton per mm square. So these are the stress induced in steel rod and copper tube. So how to find the load? Load is nothing but stress into area. So load carried by steel is nothing but stress induced in steel is equal to the cross-sectional area of the steel. We get 34042.29 Newton, and the load carried or shared by the copper tube is given by stress induced in the copper tube into its cross-sectional area. We get 15957.32 Newton. If you add these two loads, you will get the total load, which is coming out to be 50,000 Newton. And elongation, only find delta L is equal to PL by AE. Now delta LS means for the steel, PS into L by AS ES. PS by AS is written as sigma S into L by ES. We get 0.108. And similarly, you can check for a copper tube also, you'll get the same answer. Okay, that's why we are saying strain is same, and because delta L is same. Okay, so delta L by L is nothing but the strain. Next problem. A reinforced short concrete column 250 to 250 mm in section is reinforced with 8 steel bars. The total area of steel bars is 1608.50 mm square. The column carries a load of 270 kilonewton. If the modulus of elasticity for steel is 18 times that of concrete, find the stresses in concrete and steel. So write down the given data. This is a concrete column area. Total area of the steel is 1608.5. Total load is 270 kilonewton and ES is equal to 80 times EC. And area of the concrete only obtained. Area of the concrete is nothing but total concrete column area minus steel area. That gives the concrete cross sectional, concrete area 60891.5 mm square. So for composite bar, as I told you already in the previous problem, you get this expression. Okay, so you know the areas, you know the total load P, substitute, get in terms of sigma S and sigma C, and we know the strain is also same, and the problem is given ES is equal to 18 times EC, substitute it, substitute in this expression, and try to find sigma C and sigma S. Next problem, determine the changes in the length, breadth and thickness of a steel bar which is 5 meter long, 40 millimeter wide and 30 millimeter thick and is subjected to an axial pull of 35 kilonewton in the direction of its length. Young's modulus 2 to 10 power 5 newton per mm square and Poisson's ratio 0.32. And this I have represented in a diagram. Okay, so length, breadth, thickness, load 35,000 Newton. Then delta L is nothing but PL by AE. P is the force, L is the length, and this is the area 40 into 30, and E is the Young's modulus. We get 0.729 millimeter, and delta L by L is nothing but the strain 1.458 into 10 power minus 4. Poisson's ratio is equal to delta strain divided by linear strain. So delta B by B divided by delta L by L. Delta B I will find out. Poisson's ratio is 0.32. Delta L by L is given the problem, and B is also given the problem. Just multiply it. You get delta B change in breadth to be 1.866 into 10 power minus 3 millimeter. And again, Poisson's ratio is equal to delta T by T divided by delta L by L. Delta T we have to find out, that is change in thickness. T is given, delta L by L is available, Poisson's ratio is available in the problem. So after multiplication we get 1.399 into 10 power minus 3 millimeter. And volumetric strain is given by, so this is not asked in the problem. Whenever we try to calculate for this problem, volumetric strain is equal to delta V by V is equal to E into 1 minus 2 by M. So delta V change in volume is equal to E into 1 minus 2 by M into V. So E is 1.458 into 10 power minus 4 into 1 minus 2 by M. 1 by M is 0.32. Volume is length into breadth into thickness. So 5000 into 40 into 30, you get 314.928 mm cube is the change in volume. Thank you.